Bello, and today I would like to read and go along here with Chapter 14 of Basic Electricity and Electronics. Chapter 14, Inductance and RL Circuits. And this chapter starts the section 4 of the book, which is Advanced Electronic Circuits. And the introduction for this section 4, the true heart of electronics or electronic fundamentals is explored in this section. Chapters 14, 15, and 16 are very important. They cover the operation of capacitors, inductors, and their combinations in series and parallel circuits. These three chapters lay the foundation for radio and television transmission and reception. Many electrical phenomena cannot be understood without first grasping these three chapters. In Chapter 17, atomic structure is explored once more, but in more detail. Semiconductors are then introduced and explained using atomic theory. This is the foundation of solid-state electronics. Chapter 18 explains transistors, amplifiers, and electron tubes. You will see how each chapter is based on the foundation of the previous chapter. The integrated circuit has revolutionized electronics. Chapter 19 discusses digital and analog devices. There is also expanded information on the operational amplifier and the 555 timer. Chapter 20 on digital circuits details the fundamentals needed to keep up with the rapidly expanding field of electronics. Section 4 closes with a chapter on oscillators. Chapter 14, Inductance and RL Circuits. Objectives. After studying this chapter, you will be able to define the terms inductor and inductance, explain how inductance affects a current, describe an RL circuit's transient response, define mutual inductance, describe the effect of inductance in AC circuits, explain and compare true power and apparent power, use various measuring and computing methods to determine the values of currents and voltages in inductive circuits. The key words and terms will become important pieces of the electricity and electronics vocabulary. Look for them as you read this chapter. They are apparent power, Henry, impedance, inductance, inductive reactance, inductor, Lenz's law, mutual inductance, phase angle, power factor, Pythagorean theorem, reactance, reactive power, RL circuits, self-induction, time constant, transient response, true power, volt-ampere reactive or VAR, volt-amperes or VA. The study of electricity and electronics revolves around inductance, capacitance, resistance, and a combination of these in series and parallel circuits. Resistance in a circuit was studied in Chapter 3. This chapter will help you answer these questions. What is an inductor and inductance? What is the effect of inductance in a circuit? What methods are used to measure and compute values of current and voltage in an inductive circuit? Inductance. Inductance can be defined as the property in an electric circuit that resists a change in current. Again, inductance can be defined as a property in an electric circuit that resists a change in current. This resistance to change in current is the result of the energy stored within the magnetic field of a coil. A coil of wire has inductance. Some electrical items that contain coils are relays, motors, transformers, radio transmitters, radio receivers, and speakers. An inductor is an electronic component that is used to produce inductance in a circuit. Figure 14-1 shown on your screen shows the schematic symbol for an inductor, with and without an iron core. There are a number of other names for the inductor. These names include coil, reactor, and choke. Set up the experiment from Chapter 10, Figure 10-2, using the hollow coil connected to a galvanometer. Move the permanent magnet in and out of the coil and notice the deflection of the needle in the meter. When the magnet moves in, current flows in one direction. The current reverses direction when the magnet is withdrawn. No current flows unless the magnet is moved. This principle was explained in Chapter 10 in relation to the theory of generators. By moving the magnet, a voltage is induced in the coil, which causes the current to show on the meter. There is a distinct link between magnetic movement or magnet movement and the current's direction. This is an application of Lenz's law that states the field created by induced current is of such polarity that it opposes the field of the permanent magnet. A coil connected to a source of direct current builds up a magnetic field when the circuit is closed. Again, a coil connected to a source of direct current builds up a magnetic field when the circuit is closed. The expanding magnetic field cutting across the coil windings induces a counter EMF. This voltage opposes the source voltage and opposes the rise in current. When the current reaches its maximum value, there is no further change in the current. Consequently, there is no longer an induced counter EMF. The current is now only limited by the ohmic resistance of the wire. Again, the current is now only limited by the ohmic resistance of the wire. If the source voltage is disconnected, the current in the circuit falls to zero. As the current falls to zero, the magnetic field collapses. As the magnetic field collapses, it again induces a counter EMF. This counter EMF is in the opposite direction of the counter EMF created when the coil was energized. This counter EMF now retards the reduction of current. The inductance of the coil resists any change in current value. The symbol for inductance is L, capital L. Inductance is measured in a unit called a Henry, symboled with a capital H. A Henry represents the inductance of a coil if 1 volt of induced EMF is produced when the current is changing at the rate of 1 ampere per second. Again, a Henry represents the inductance of a coil if 1 volt of induced EMF is produced when the current is changing at a rate of 1 ampere per second. This is expressed mathematically as shown on the screen, the equation where E equals the induced voltage, L equals the inductance in Henrys, and delta I equals the change in current in amperes, and delta T equals the change of time in seconds. Note that the symbol delta means a change in. Producing stronger and weaker magnetic fields. The strength of an induced voltage depends upon the strength of the field, and that a stronger magnetic field produces a higher induced voltage. This magnetic field can be strengthened by inserting a core in the coil. An iron core has higher permeability than air and concentrates the lines of force. This concept was explained in the study of magnetism in Chapter 9. Large inductors are most often wound on laminated iron cores. Their inductance is measured in Henrys. Smaller inductors used in circuits that operate at higher frequencies can have powered iron or iron cores, can have powered iron or air cores. They have inductance measured in millihenries, 1/1000th of a henry, and microhenries, 1/1,000,000th of a henry. Radio frequency chokes using air cores are shown in figure 14-2 shown on the screen. The core material is just one factor that affects the size of the inductance produced by the coil. Figure 14-3, which is shown on your screen, is a chart of diagrams, a chart that diagrams inductor traits that can strengthen or weaken a coil's inductance. 14-3, chart of some of the factors that affect a coil's inductance. Self-induction. A changing current through an inductor produces an expanding or collapsing magnetic field cutting across the wires of the coil. A counter EMF is induced that opposes the change in current. This action is called self-induction. The strength of the self-induction depends on the number of turns of wire in the coil, the length between the length of the coil and its diameter, and the permeability of the core. Transient responses. The response of the current voltage in a circuit after an instant change is applied voltage. The response of the current and voltage in a circuit after an instant change in applied voltage is known as a transient response. Again, the response of the current and voltage in a circuit after an instant change in applied voltage is known as a transient response. A coil is connected to a DC voltage source. Refer to the diagram 14-4 shown on the screen now. When the switch is closed, the current builds up gradually. This effect is due to the inductance of the coil and the internal resistance of the battery. When the switch is opened, the current decays in a light manner. The rise and decay of the current in this circuit is shown in the graph in figure 14 shown on the screen now. It is important to understand that the opposition to the rise and decay of current occurs only when there is a change in applied voltage. Again, the opposition to the rise or decay of current occurs only when there is a change in applied voltage. When there is no change, the current remains at its steady state value. This steady state value depends only on the resistance of the coil. A resistance is joined in series with an inductor in the circuit in figure 14-6. Figure 14-6 view A, as you can see on the screen. A circuit that contains resistance and inductance is called an RL circuit. The action of the voltage and current should be studied for increases and decreases. For example, when the switch is closed, the counter EMF of the coil, L, equals the source voltage. As you can see in view B, in the middle of the screen, since no current has started to flow, the IR drop across R equals 0. As the current gradually builds up, the voltage ER increases, and counter EMF EL decreases until a steady state condition exists. All the voltage drop is ER, and there is no drop across L in view C at the bottom. As you can see in figure 14-7, if the RL circuit is shorted by another switch, such as in view A, the stored energy in the field of L instantly develops a voltage, view B. at the bottom. This voltage is of the opposite polarity of the applied voltage. The circuit is discharged by current flowing through R. The graphs showing the charge and discharge of the circuit appear in figure 14-8. Here in figure 14-8, the baseline or x-axis of these graphs represent time. The transient response of an RL circuit does require a certain amount of time. The amount of time to complete the transient response depends upon the values of R and L in the circuit. This value is called the time constant, represented by a small t of the circuit. For an RL circuit, it is found using the following formula. Looking at the formula, T equals L divided R. L is measured in henries and R measured in ohms, where T equals the time in seconds for the current to increase to 63.2% of its maximum value or to decrease to 36.7% of its value. In most cases, a circuit is considered fully charged or fully discharged after a period of 5 time constants. You can see in figure 14-9 top, the graph is showing the percentage of full charge against the number of time constants. From this graph, you can see why 5 time constants is considered full charge or discharge. The bottom of the figure 14-9, as you see on the screen, is a chart giving the voltage at the end of each time constant, assuming the source is 100 volts. At this time, please perform review questions for section 14.1. Mutual inductance. When two coils are within magnetic reach of each other, so that the flux lines of one coil link with or cut across the other coil, they have mutual inductance. If the coils are close to each other, many magnetic lines of flux from the first coil will link with the second coil. On the other hand, if the coils are at a distance apart, there might be very little linkage. The mutual inductance of two coils can be increased if a common iron core is used for both coils. The degree to which the lines of force of one coil link with the windings of the second coil is called coupling. If all lines of one cut across all the turns of the other, we have what is called unity coupling. Any number of percentages of coupling can exist due to the mechanical position of the coils. The amount of mutual inductance can be found using the formula shown on the screen. Lm equals K the square root of times the square root of L1 times L2. Well, where Lm is the mutual inductance in henries, K is the coefficient of or percentage of coupling, and L1 and L2 are the inductances of the respective coils. Mutual inductance must be considered when two or more inductors are connected in series or parallel in a circuit. Phase relationship in series and parallel inductance. When coils are joined in series, the total inductance is, as shown on the screen, the top, LT equals L1 plus L2 plus L3, and so on. Notice that the individual inductances add together like series resistors. However, when there is mutual inductance, the formula becomes, such as at the bottom, LT equals L1 plus L2 plus, more or less, plus or minus, 2Lm. Again, LT equals L1 plus L2 plus or minus 2Lm. The plus or minus sign before the 2Lm means that the mutual inductance value might be added or subtracted depending on whether the magnetic fields are aiding or opposing each other. The plus should be used when the coils aid each other. The minus should be used when the coils oppose each other. When inductors are connected in parallel without mutual inductance, the total inductance can be calculated using the formula on top of the screen. 1 over LT equals 1 over L1 plus 1 over L2 plus 1 over L3 and so on. The formula is structured the same way as the parallel resistance formula. When only two inductors are being added in parallel, the products over the sum formula can be used. See the formula on the bottom of the screen. LT equals L1 times L2 divided by L1 plus L2. Notice that here again, inductors in parallel add like resistors in parallel. Mutual inductance is widely used in electricity and electronics. A skilled technician must have a complete understanding of the characteristics of circuits containing these components. Now please review questions for section 14.2. 14.3 Inductance in AC circuits. In an AC circuit, the applied voltage constantly varies and reverses polarity. Any inductance in the circuit will generate a counter EMF, which will oppose the source voltage. Again, any inductance in the circuit will generate a counter EMF, which will oppose the source voltage. This event can be observed by setting up the experiment in experiment 14-1 again. Connect a light to a 6-volt DC source. Note its brilliance. Now connect the light to a 6-volt AC transformer and note its brilliance. Is it brighter or dimmer? The inductance has some indirect effect on the current. Opposition to an alternating current due to inductance or capacitance is called reactance. Again, opposition to an alternating current due to inductance or capacitance is called reactance. The letter symbol for reactance is X. When reactance is caused by an inductor, it is called inductive reactance. Inductive reactance is measured in ohms, and its symbol is XL. Induced current voltage. Induced current and voltage. Remember that the induced voltage in a coil is the counter EMF. The induced voltage in a coil is the counter EMF. Counter EMF opposes the source. Again, counter EMF opposes the source. Therefore, it is 180 degrees out of phase with the source voltage. This counter EMF opposes change, and the greatest counter EMF is induced when the current change is at a maximum. See figure 14-10 on your screen. The greatest rates of change of current is at 90 degrees and 270 degrees. Again, the greatest rate of change of current is at 90 degrees and 270 degrees. At these points, the applied voltage must be at a maximum. The applied voltage must be at a maximum. The induced voltage is also at a maximum. At 180 degrees and 360 degrees, the current change is minimum. The current is at its maximum value, ready to start its decline. As you can see in figure 4-10 on your screen, in a circuit containing pure inductance, the current is 90 degrees out of phase with the applied voltage. The current is lagging behind the voltage. The magnitude of the reactive force opposing the flow of AC is measured in ohms. It can be Mathematically, using the following equation, XL equals 2 pi FL, where XL equals inductive reactance in ohms, F equals frequency in hertz, L equals inductance in henries, and pi is approximately 3.1416. Remember, as frequency or inductance is increased, the inductive reactance increases. They are in direct proportion. Again, as frequency or inductance is increased, the inductive reactance increases, and they are in direct proportion. An inductance in a circuit behaves differently as various frequency signals are applied. In your screen, an 8 Henry inductor connected to a DC F equals 0 signal has a reactance of 0. This means the 8 Henry inductor does not impede the DC signal at all. Using the formula XL equals 2 pi FL, the reactance can be computed for frequencies of 50, 100, 500, and 1000 Hz. A partial graph of the results show the linear increase of reactance as the frequency is increased. In the figure on your screen, the frequency has been held constant at 1000 Hz. The reactance is plotted as the inductance is increased from 0 henries to 0.8 henries. Notice the linear increase in reactance as the inductance is increased. These principles can be applied to filter and coupling circuits. However, you must first understand the traits of reactance and how they change as a result of inductance and frequency of the applied voltage. Power in inductive circuits. Power consumed in a purely resistive circuit is the product of the voltage and current, which is P equals I times E, or power equals current times voltage. This is the actual power used by a circuit. It is called true power, and it is given in units of watts. However, in an AC circuit containing inductance only, this formula does not hold true. In this type of circuit, a current will flow bound to the reactance of the circuit. Again, in this type of circuit, the current will flow bound by the reactance of the circuit. The power used to build the magnetic field is returned to the source when the field collapses. This is reactive power. Reactive power is measured in VARs, or VARs, which stands for volt ampere reactive. Again, the power used to build the magnetic field is returned to the source when the field collapses. This is reactive power. Reactive power. Reactive power is measured in VAR, which stands for volt ampere reactive. The combination of true power and reactive power gives rise to a measure of power that appears to be delivered to a load. This power is called apparent power. Again, the combination of true power and reactive power gives rise to a measure of power that appears to be delivered to a load. This power is called apparent power. It is equal to the product of the effective voltage and the effective current. Again, apparent power is equal to the product of the effective voltage and the effective current. Apparent power is measured in VA, or volt amperes, as shown in the equation on your screen. For example, if a 100 E effective power is applied to a certain inductive circuit, this causes a I effective or effective current of 10 amps. The apparent power equals to apparent power equals to 100 volts times 10 amps, which equals to 1000 VA. Remember, watts are not used for apparent power. The power factor. The ratio of true power to apparent power in an AC circuit is called the power factor, or PF. Again, the ratio of true power to apparent power in an AC circuit is called the power factor, or PF. It has no units. It can be calculated using trigonometry. The power factor is equal to the cosine of the phase displacement between the current and voltage, and the formula is shown on your screen, where theta is the phase displacement. Note that by rearranging this formula, add the formula for true power shown on your screen, where true power equals apparent power times cosine theta, or true power is equal to effective voltage times effective current times cosine theta. As an example, assuming our previous circuit is purely inductive, determine the power factor and phase displacement. PF, or power factor, equals cosine theta equals 0 watts divided 1000 VAs, which equal 0. The power factor in this case is 0. The angle whose cosine is 0 is 90 degrees. This tells us that the current and voltage in the purely inductive circuit are 90 degrees out of phase. And here you can see how the current and voltage in the purely inductive circuit are 90 degrees out of phase. That is shown on your screen now. A circuit containing inductance only, again, the true power is 0 and the current lags voltage. The current lags the voltage by 90 degrees. If an AC circuit contains only resistance, the current and voltage are in phase. Figure 14-14, as shown on the screen. The power consumed is equal to I times E, or current times power, even though the polarity of the voltage changes and the current reverses, positive power is consumed. A resistor consumes the same amount of power no matter which direction the current is moving. The power factor in a circuit of this type equals 1. The apparent power is equal to the true power. The circuit traits change when an inductor is added in series with the resistor. The component does not have to be a resistive component. The wire from which the coil is wound will have a certain amount of resistance. In figure 14-14, a purely resistive circuit, true power and apparent power are the same. The current and voltage are in phase. Now referring to figure 14-15 on the screen, the series resistance equals 300 ohms. The inductive resistance equals 400 ohms. This reactive component will cause the current to lag by an angle of 90 degrees or less. The forces opposing the current can be thought of as the resistance and reactance. The resistance and reactance are 90 degrees out of phase. To find the final opposition, the combination of resistance and reactance, add the vectors of the two forces. For that, refer to figure 14-16. Again, to find the final opposition, the combination of resistance and reactance, add the vectors of the two forces. as you see on the screen, that figure 14-16. Vector addition of XL and R, which are 90 degrees out of phase. Here the vectors can be added using the graph. Place the tail of the XL vector on the arrowhead of the R vector. Again, place the tail of the XL vector on the arrowhead of the R vector. Then draw a vector from starting points of the resistance vector to the head of the reactance vector XL. Again, draw a vector from the starting point of the resistance vector to the head of the reactance vector XL. This new vector shows the magnitude and direction of the combined forces. The angle between this new vector and the resistance vector is theta, as seen in figure 14-16 in your screen. The total opposition to an alternating current in a circuit having resistance and reactance, the new vector you just have created, is the impedance. Again, the total opposition to an alternating current in a circuit having resistance and reactance is the impedance. The symbol for impedance is Z, capital Z, and it is measured in ohms. Impedance problems are commonly solved using the Pythagorean theorem. The theorem is shown on the screen, stating that the hypotenuse of a right triangle is equal to the square root of the sum of the squares of the two sides. It is written as shown on the screen, where C is the hypotenuse and A and B are the other two sides of the right triangle. In the problem figures 14-15 and 14-16, XL equals 400 and R equals 300. Find the impedance Z. Using the formula, Z equals the square root of R squared plus XL squared. That's the Pythagorean theorem. Z equals to the square root of 300 ohms squared plus 400 ohms squared, which is equal to 90,000 ohms plus 160,000 ohms. All square rooted, which Z is equal to 500 ohms. The impedance of the circuit is 500 ohms. The angle between the vector Z and the vector R is called the phase angle, theta. It represents the phase displacements between the current and voltage resulting from the reactive component. So, since cosine theta equals the power factor, cosine theta equals power factor again, cosine theta equals R divided Z, or cosine theta equals R divided Z, which equals 300 divided 500, which equals 0.6. Since the cosine of theta equals 0.6, the angle whose cosine is 0.6, 53.1 degrees approximately, is equal to the phase angle. Therefore, the current lags the voltage by an angle of about 53.1 degrees. The true power in this circuit can be now calculated. The true power in this circuit equals to the apparent power times the power factor, or cosine theta. The true power equals I equals E divided Z, which equals 100 volts divided 500 ohms, equals 0.2 amps. The apparent power equals E times I, or voltage times current, which is the apparent power equals 100 volts times 0.2 amps, which equals 20 volt amps, VAs. The true power equals volts times current times cosine theta. True power equals 100 volts times 0.2 amps times cosine 53.1 degrees. And true power equals 20 watts times 0.6, and the true power equals 12 watts. (14-17) The relationship between voltage, current, and power in the circuit are described in the text. These figures can be checked by inserting them into the power factor formula, which is PF, power factor, equals true power over or divided by apparent power. PF equals 12 watts in this case, divided 20 volt amps, which equals 3 over 5, which equals 0.6. The power factor is not only considered in theory, but in practice. The power factor must be considered whenever a power company connects power lines to a manufacturing plant. Industries must keep the power factor of their circuits and machinery within specified limits, or pay the power company a premium. The reactive power is sometimes called wattless power. It is returned to the circuit. In figure 14-17, the power in the shaded area above the zero line is used. The power below the line is wattless power. Ohm's law for AC circuits. In computing circuit values in AC circuits, Ohm's law is used with one exception. Z is used in place of R. Again, in computing circuit values in AC circuits, Ohm's law is used with one exception. Z is used in place of R. Z represents the total resistive force opposing the current. Therefore, as shown on the screen, current equals power or voltage times Z, or I equals E divided Z, and E equals I times Z, and Z equals E divided I. Again, Z is used instead of R. Example, a series circuit contains Henry choke, contains an 8 Henry choke, and a 4,000 ohm resistor. Again, a choke is an inductor. So in this example, an 8 Henry choke is used and a 400 ohm resistor. It is connected across a 200 volts 60 Hz AC source. Find the impedance, circuit current, voltage drops across the resistor and inductor, phase angle theta, apparent power, and true power. See figure 14-18 as shown on your screen. This is how you work it out. First, find the reactance of L at the top of the screen. XL equals 2 pi FL, formula discussed earlier, which is equal to 2 times 3.14 times 60 Hertz times 8 Henry, which is equal to 3014 ohms, or 3000 ohms approximately. Then find the impedance of the circuit. Z, representing impedance, equals the square root of R2 plus XL2, or R squared plus XL squared. And as you can see, it's 5000 ohms. Then you find the current in the circuit, or I equals E divided Z, or 200 volts divided 500 ohms, which equals 0.04 amps. Then find the voltage drop across R and XL using the formula ER equals I times R, or 0.04 amps times 4000 ohms equals 160 volts, and EXL equals 1 times XL, or 0.04 amps times 3000 ohms equals 120 volts. Notice that the sum of the voltage drops does not equal the applied voltage. This is because the two voltages are 90 degrees out of phase. This requires a vector addition. The source voltage, ES, as shown on the screen, source voltage ES equals the square root of 160 volts squared plus 120 volts squared, which, as you can see, equals to ultimately 200 volts. To find the phase angle theta between I and E, you use the formula cosine theta equals R over Z, or divided Z, which is 4000 ohms divided 5000 ohms, which is 0.8. 0.8 is the cosine of an angle of 37 degrees. Theta equals 37 degrees. To find the true power and apparent power is I times E, which is 0.04 amps times 200 volts, or 8 volt amps. The true power is I times E times cosine theta, which is 0.04 amps times 200 volts times 0.8, or 6.4 watts. Note that some figures have been approximated to make the calculation simpler. RL circuit. In a circuit containing a resistance and an inductance in parallel, the voltage of each circuit element is the same as the source voltage. Further, there is no phase difference among the elements because they are all in parallel. There will, however, be a phase difference among the total and branch currents. The current is in phase with voltage in the resistive branch. Current lags the voltage across the inductor by 90 degrees. The total current will lag the source voltage by some angle between 0 and 90 degrees. If the reactance of the inductor is larger than the resistance of the resistor, the angle will be closer to 0 degrees. If the resistance is much larger than the reactance, the lag will be closer to 90 degrees. In the parallel RL circuit, we do not find impedance through a vector sum. Instead, we apply Ohm's law, which is shown on the screen as Z equals ES over, or divided by, IT. As discussed, voltage in the parallel RL circuit is in phase with IR, and it leads IL by 90 degrees. Thus, we can say that IR leads. So, as discussed, voltage in the parallel RL circuit is in phase with IR, and it leads IL by 90 degrees. Thus, we can say that IR leads IL by 90 degrees. The parallel RL circuit then has two current components, IR and IL. Both of these can be represented by phasors. Since they are out of phase, we cannot simply add the two components together to figure the total circuit current. We must find their phasor sum. See figure 14-19, which is shown on your screen. Again, voltage in the parallel RL circuits, it's in phase with IR and it leads IL by 90 degrees. Thus, we can say that IR leads IL by 90 degrees. The parallel RL circuit then has two current components, IR and IL. Both of these can be represented by phasors. Since they are out of phase, we cannot simply add the two components together to figure the total circuit current. We must find the phasor sum. See the figure on your screen, which is the equation IT equals the square root of IR squared plus IL squared. Lags voltage, the horizontal reference for the parallel RL circuit. Since a phasor or rotating vector rotates counterclockwise, a lagging phasor would be behind or clockwise to a leading phasor. The phase angle represents the phase displacement between current and voltage resulting from a reactive circuit element. For the parallel RL circuit, the phase angle is found on the current phasor diagram. The horizontal reference of this circuit is voltage, since it is common to all circuit elements. In the current phasor diagram, we do not have a voltage phasor. We use IR as the horizontal component since it is in phase with voltage. Figure 14-19, using the diagram, the phase angle can be found from the equation shown on the bottom here on the screen. Theta equals arctan times IL divided IR. As an example, using the circuit in the assigned values in figure 14-20, the circuit with the assigned values in figure 14-20, as you can see on the screen. Determine the phase angle between applied voltage and current. Draw the current phasor diagram and find the circuit impedance. Again, to compute this problem, step 1 is to compute the value of inductive reactance, or XL, shown as the formula. XL equals 2 pi FL, which is 6.28 times 100 Hertz times 4 Henries, which equals 2512 or 2512 ohms. Step 2 is to compute the branch currents using Ohm's law. IR equals ES divided R, or 100 volts divided 1500 ohms equals 0.67 amps, 0.067 amps. IL equals ES divided XL, which is equal to 100 volts divided 2512 ohms, which equals 0.04 amps. Step 3, determine the phase angle to see how much the circuit current lags the voltage. And is computed using the following. Theta equals arctan times IL divided IR, which equals arctan 0.04 amps divided 0.067 amps. Arctan theta is then equal to arctan 0.597, which is equal to theta equals to 30.8 degrees. Step 4. Draw the current phasor diagram. Use any convenient scale. Remember that IR is drawn as the horizontal component. IL is drawn downward at 90 degrees from IR since it lags voltage. The horizontal reference, see figure 14-21. Step 5. Find the total circuit current. You can use IT equals the square root of IR2 plus IL2, which equals to the square root of 0.067 amps squared plus 0.04 amps squared. Step 4 would be to draw the current phasor diagram. Use any convenient scale. Remember that IR is drawn as the horizontal component. Excuse me, IL is drawn downward at 90 degrees from IR since it lags voltage. The horizontal reference, see figure 14-21. Step 5, find the total circuit current. IT equals the square root of IR2 plus IL2, which equals to square root of 0.067 amps squared plus 0.04 amps squared, which equals to 0.078 amps. Step 6 would be to find the impedance of the circuit. Using Ohm's law, Z equals ES divided IT, which equals 100 volts divided 0.078 amps, which is 1282 ohms. Once again, it is important to understand the various quantities would be that how the various quantities would be affected by a change in frequency. The effects of change in frequency are summarized in figure 14-22 as shown in. It shows how values change in a parallel RL circuit as frequency is changed and inductance is held at a constant value. Now you can go ahead and review the questions for section 14.3 and perform those questions. Page 221, top left. And the summary for this chapter. Inductance is the property of a circuit. Inductance is that property of a circuit that opposes any change in current. An inductor is a component that produces inductance in a circuit. Other names for an inductor are coil, reactor, and choke. The unit for inductance is the Henry, symbolized by capital H. Some factors that affect the amount of inductance are the number of turns of coil, diameter of coil, core material of the coil, type of winding, spacing between the windings or the length of the coil, and the size of the wire. The time constant of a coil is the amount of time it takes for the current to rise from 0 to 63.2% of its maximum value. The formula for time constant is T equals L in henries divided R in ohms. Mutual inductance is two or more coils linked by magnetic lines of flux. The following formulas are used to compute inductance in a circuit. Inductor in series equals to LT equals to L1 plus L2 plus L3 and so on. Inductors in parallel are computed using 1 over LT equals 1 over LT1 plus 1 over L1 plus 1 over L2 plus 1 over L3 and so on. Or a shortcut when only two inductors are in parallel is the formula LT equals L1 times L2 divided by L1 plus L2. Inductive